Welcome to The Explainer. We're about to dive into the language that scientists literally use to describe the universe. And it's not just about numbers. Think of it more like a grammar for reality itself.
All right, let's kick things off with a pretty simple question. Just think about it for a second. Can you really measure everything?
Well, in physics, the answer is a hard no. You can totally measure, say, the length of a room, right? But can you measure love? Nope. And that's the key. Physics can only deal with stuff it can measure. We call these things physical quantities, and they're basically the nouns in this whole new language we're about to learn.
Okay, so how does this language of measurement actually work? Well, every single physical quantity has two parts, two absolutely essential parts. You can't just throw out a number and call it a day.
Think about it. If I told you my weight is 60, you'd be like, 60 what, right? Grams? Pounds? Tons? See? The number, 60, that tells you how much. But the unit, like kilograms, that tells you of what. You need both. Without both, the measurement is totally meaningless.
Okay, now this is where things get, well, kind of mind-blowing. The entire massive, complex world of physics, it's all built on just 7 basic units. That's it. We call them fundamental units, and seriously, you can think of them as the alphabet of the universe.
Yep, these 7 right here. That's the whole shebang. Mass, length, time. You see them on the screen. And get this, every other measurement in all of physics, I'm talking from the speed of your car to the energy blasting out of a star, it's all just a combination of these 7 basic letters.
So if those 7 are our letters, what happens when we start putting them together? Well, we start making words, right? And in physics, we call these words derived units.
Let's take speed, for instance. It's a perfect example. There isn't a fundamental unit for speed. Nope. We have to derive it. And we do that using 2 of our alphabet letters. Distance, which is really just length, and time.
And this shows you exactly how it works. We literally just combine the units of the parts. So the unit for length, that's meters. Divide that by the unit for time, which is seconds. And boom, meters per second. That's our new derived unit for speed. Simple as that.
And this works for way more complex stuff, too. Take force. Force is just mass times acceleration. So what do? We just combine the units. We take the kilogram for mass, and we multiply it by the units for acceleration, which happens to be meters per second squared. See? It's just like building a more complicated word from our very simple alphabet.
Okay, so we have letters, we have words. What about sentences? Equations. How do we make sure our physics sentences are actually correct, that they make sense? Well, there's a kind of universal grammar checker for that. It's called dimensional analysis.
And the main rule here is actually super simple. It's something you already get intuitively. You can't add 10 kilograms to 10 centimeters, can you? It's just nonsense. It doesn't compute. The units are what we call their dimensions. They have to match. You got to compare apples to apples.
We can use this idea to check pretty much any equation. Let's look at this classic one for distance. We just check the dimension of each piece of the equation, one by one. So S is distance. Its dimension is length. Easy. Now UT, that's velocity times time, which actually simplifies down to length. And AT squared, well, we can ignore the number 1/2 because numbers don't have dimensions. And guess what? It also simplifies to length. So look at that. Every single term has the dimension of length. Our grammar checker gives it a big thumbs up. The equation is legit.
But here's where it gets really powerful. This is the cool part. We can use dimensional analysis not just to check formulas, but to actually build them from scratch with nothing but logic.
All right, let's give it a shot. Imagine we want to figure out the formula for how long it takes a pendulum to swing back and forth. Let's just assume for now that it only depends on 2 things, how long the string is and the acceleration due to gravity, g. Okay, so here's the game plan. First, we just say that the time period t is related to the length raised to some unknown power x and gravity raised to some other unknown power y. Then we just translate that into the language of dimensions. On the left, we have the dimension of time, and on the right, we have a mix of length and time dimensions from our L and G.
Now, here's the trick. For this whole thing to make sense, to be grammatically correct, the powers for each dimension have to be the same on the left and the right. This lets us set up a couple of really simple little algebra problems. We just match up the powers for time and match up the powers for length, and we can solve for those mystery numbers x and y.
And once we have x and y, we just plug them back into our first guess. And what do you know? Just like magic, the real formula for a pendulum swing just appears. We literally figured it out just by using logic and the rules of our physics grammar. Now, the one thing this can't tell us is that constant k out front, because it doesn't have any dimensions, but still, pretty amazing, right?
All right, last thing. Let's talk a little bit about the etiquette, I guess you could call it, of this language. How do we communicate our measurements honestly? How do we make sure we're not claiming we're more precise than we actually were? Well, we do that with something called significant figures.
Basically, significant figures are just the digits in a number that actually mean something, the ones you can rely on. And the rules for figuring them out are pretty simple. Any non-zero digit, it's significant. Zeros that are sandwiched between other digits, they're significant too. But those leading zeros at the beginning, they're just placeholders. They don't count. Now, trailing zeros at the end, that's the tricky one. They only count if you see a decimal point somewhere in the number. That decimal is a little signal that says, hey, I measured this precisely.
Let's just look at a few examples. It makes it way easier. See 48,923? All 5 of those digits are important. Now look at 0.0004. Here, only the 4 is significant. The other zeros are just there to hold the place. But then you have 3.90. That 0 at the end, it is significant, all because of that decimal point. It's telling us the measurement was precise right up to that hundredths place.
So what's the big takeaway from all this? It's that when you understand units, dimensions, and even significant figures, you're not just doing math problems, you're actually learning to speak the language of physics. You're learning the grammar of reality itself.
And that's a pretty powerful idea, isn't it? If we can literally derive fundamental laws of nature just by checking our grammar, it makes you wonder, what other secrets are just hiding out there in plain sight, waiting for us to find the right language to describe them? Anyway, that's something to chew on. Thanks for watching.